Hello everyone, welcome to this video on an important concept in linear algebra and quantum mechanics. Today we'll explore the proof that the eigenvalues of a matrix remain unchanged under a unitary transformation. So before starting this important derivation, let's go to the definition of unitary matrix and eigenvalues and eigenvector. So what is unitary matrix? Unitary matrix is a matrix whose under multiplication by its Hermitian transpose gives an identity matrix. So to understand this, let's look what is conjugate transpose or Hermitian transpose. To understand this better, let's take an example A. So the Hermitian transpose is written as Hermitian transpose of A is the conjugate of a matrix obtained after transposing a matrix. So this is the Hermitian transpose. In other words, it is A dagger. If A dagger when multiplies with A gives an identity matrix I, then A is called unitary matrix. So how to calculate conjugate of any matrix? I mean, how to calculate the Hermitian transpose of any matrix? So let's take an example of this case. Here A is a complex matrix which has the complex elements like this. So first of all, in order to calculate AH or Hermitian transpose of A, we calculate its transpose. So how do we calculate transpose? We just change the row with columns. So its transpose will be 1 plus y and 5 plus I, 3 minus y and 7. I've just changed the row with columns. Now to calculate its Hermitian transpose, you have to calculate the conjugate of this transpose of A. So this becomes 1 minus 2y, 5 minus I, changing the sign in parts, 3 plus 4y and 7. This is the Hermitian transpose or the complex conjugate transpose of the matrix A. So this is the way how we calculate the Hermitian transpose. So U is a unitary matrix whose Hermitian transpose when multiply with itself gives an identity matrix. Identity matrix is a matrix whose all diagonal elements are 1 and other all elements are 0. Now let's talk a little bit about eigenvalue and eigenvector also. An eigenvector B of a matrix A is a non-zero vector. B is a non-zero vector that when multiplied by A, that is when that vector is multiplied by a matrix, the result is the scalar multiple of the same vector. This is a matrix, this is a vector, this is a vector, and when a vector, non-zero vector, is multiplied by a matrix, that results a vector multiplied by a scalar. That scalar is eigenvalue of this A, and B is its corresponding eigenvector. Now let's look closely to the unitary transformation of matrix A. So as we have defined, U is a unitary matrix. If I write U dagger A and U, this gives me the unitary transformation of a matrix A. Let us say that is B. Now in order to prove our hypothesis, we have to show that B and A where B is the unitary transformation of A, both should have the same eigenvalue. Let's move ahead to prove that, and let's start from the eigenvalue equation of B by supposing mu as the eigenvalue of matrix B and W as its corresponding eigenvector or the eigenstate. So we can just simply replace B with this thing to get this expression. And now let us multiply this equation by the unitary matrix U from left side. We get this expression. If we separate this first two, U and U dagger, our expression will be something like this. And since, if you remember, we have defined U as a unitary matrix, and unitary matrix is a matrix when it multiplies with its Hermitian conjugate, that gives us an identity matrix. So this part becomes I, and this expression converges to this expression. Here I have just arranged the U's position. So if you look closely to this equation, we can see that A multiplies with this factor and mu multiplies with this factor on both sides. Let us say this is B. In other words, let U multiply with W is B. Then we get this expression, that is A when multiply with a vector B gives some scalar mu times the same vector B. This means B is the eigenvector and mu is the eigenvalue of matrix A. In other words, from this equation and this equation, we have seen that mu is the eigenvalue of both A as well as B with their corresponding eigenvector B and W. This proves that A and B both have the same eigenvalue. In summary, we have demonstrated that the eigenvalues of a matrix A remain unchanged under a unitary transformation. This proof highlights the power of unitary operations in preserving important properties of matrices, which is fundamental in both linear algebra and quantum mechanics. Thank you for watching this presentation. I hope you found it informative and helpful. If you have any questions or comments, please feel free to leave them below. Don't forget to like, share and subscribe for more educational content. See you in the next video.